So part 2 here is really a continuation of what we did last Wednesday. Just want to show you a couple more examples. So take a look. Lipitor is supposed to reduce cholesterol. They did a trial, and 19 out of 863 patients complained of having flu symptoms. We know just on past experience that people taking this sort of drug, 1.9% of them have flu-like symptoms. So here's the question. Based on our sample, do we think more than 1.9% of Lipitor users have those symptoms? So hypothesis test, right? And they're saying alpha, the level of significance, is 1%. That means we have to show that the results we got are less than 1% of the time by chance. All right, so the first thing we do is find p hat. And this is what I'm getting. Now, just based on this sample, we got 2.2% having those symptoms. Can we just say right off the bat, yeah, more Lipitor users have more than 1.9%? No. We did in this sample, but in general, that doesn't prove it. All right, so let's do our hypotheses. First one, the null hypothesis is always there is no difference, everything's the same, the status quo. So we're going to put this. We're going to say P equals 1.9%. Now that P stands for what? A population proportion, but which population? Just our population in general or the population of Lipitor users? Right, Lipitor users. Because that's what we're interested in. You've always got to nail down the population you're talking about. So we're talking about Lipitor users here. Alternatively, we think maybe more than 1.9% get those symptoms. So this is a one-sided test. I put greater than there. Before you ever do the test, before you ever get a sample, you're going to know what your hypotheses are. Otherwise, why are you doing the test? So far, so good? Next thing, we need to check the conditions. Okay. We get a sample and then we say, was it random? Well, this was a clinical trial, so yeah, let's assume that it was. Next thing, we're talking about a distribution that's normal enough. And so we do that NP times 1 minus P thing. And I'm getting this. 18.6 is greater than or equal to 10. So yeah, normal enough. Last one, were the people in our sample independent of each other? And for that, we use the 5% rule. So I know 863 people is way less than 5% of Lipitor users. I mean, there's thousands and thousands and thousands of Lipitor users. Okay, so we jump through all three hoops. We think we might have a valid sample here. Next thing we do is get a z-score. So z sub 0. Now notice that 0.019 appears 3 places. That's our null hypothesis. I think the last set of notes, I put that in red, but this time that 0.019 is what we're saying for the null hypothesis. Why? Because we're assuming it's true. The whole logic is, assuming the null is true, what kind of results did we get? So when I get this z-score, here's what I got. See if you get the same thing, please. So that means based on our sample proportion is 0.65 standard deviations away from what the null is saying. Just looking at that in standard deviations, does that seem like a rare occurrence to you? No. It's not even one standard deviation away. So just on the surface, it looks like, yeah, no, that's not rare enough. So then we get our critical value. Now this is the classical approach. We get our critical value. This is at the 1% level for alpha, right? How do you find the critical value? You get your formula pages out. So go ahead and do that if you would, please. And you're going to try and find a z-score for alpha. So since alpha is 0.01, you're trying to find an area on the right-hand side now, right? So you're looking for what? As close to 0.99 as you can get? This is a greater than test, so we're using the right-hand side, z alpha divided by 2. What you getting? That's what I got. So if you didn't get 2.33, look at the z-score 2.33 and then go out to the area and see if that's pretty close to 0.01. Should be positive because this is a greater than test. And that's a good question. Look at our z sub 0. It's positive, 0.65. Good question. This one I just got from our sample. This one, they told us alpha is 0.01. So then I get my formula pages out, and I know it's going to be on the right-hand side. So I want 0.01 to the right of it, which means in my formula pages, I'm looking for an area of close to 0.99 as I can get. Check and see if that's what you're getting when you do that. Okay, with the classical approach, all we do is compare z-scores, right? The z-score we got is 0.65. Our cutoff line is 2.33. If our z-score is bigger than that, we reject the null. It's nowhere close to being bigger. So our decision is, here's my little drawing. Sure doesn't hurt to make a little sketch like this. It lets you see where z sub 0 is in relationship to z alpha. That means to the right of z alpha is 1% of the area, right? If our z-score had ended up out here to the right of z alpha, out here someplace, what would we do? We'd reject the null because we're saying, no, that's too far away. But we're back in here. So the logic is, since the z-score from our sample is not larger than z alpha, we can't reject the null. We don't have enough evidence to reject the null. Said another way, our z-score would have to be bigger than 2.33. If it come out to be 2.5, then we'd be rejecting the null because we're out there in reject territory out in here. All right, so we made a decision, and then all's left is to write the conclusion. You don't have to word it exactly like this, but just notice what I'm putting in here. I'm putting the level of significance, whether I'm going to reject the null or not, and what the null is saying. One sentence. I know it's a long sentence, but I'm saying we don't have enough evidence at alpha at the 0.01 level. to be able to reject the null hypothesis. And then I just restate what the null hypothesis is. Might not be the greatest conclusion in the world, but it's a conclusion that tells you what's going on. You don't need to write a novel there. It was a dark and stormy night. That is a complete hypothesis test. Look what we did. We read the problem. We saw what alpha was going to be. We did our hypotheses. That's before you ever do the actual test. And then you get a sample. You check to make sure all the conditions were met. If they weren't, then you need to go get another sample. You should know ahead of time how many you need in the sample based on what we did in chapter 8. Then we did what? We got a z-score. We got a critical value. We compared those two and made our decision based on whether our z-score from the sample was bigger than the critical value. Then we wrote a conclusion. That's it. Those are the steps of a hypothesis test. Questions, y'all? Oh, let's do a p-value approach. Now, remember, the difference between a p-value approach and the classical approach is the p-value is just a probability, which means the hypotheses, the conditions, and the z-score, they're all the same. You're going to use that z-score from your test, from your statistic, to determine things. Okay. So how am I getting this p-value? I look at the z-score, 0.65, and then in the area part, I see how much area is to the right of that. So I look up the z-score, 0.65. When I did, I got 0.7422. But I'm talking about to the right of that, so I've got to subtract it from 1. Why? Because this is a one-sided test that is testing for greater than the null. Okay, when I subtract that, I'm getting this for a p-value. What's a p-value even represent? Yes, sir. Probability of what? The probability of being as far out as the results we got are further out. They're saying, what's the likelihood of getting results like you did or even more extreme? That's what a p-value is. And what's this telling us? Well, about 26%. Stop writing for just a second. Just think a minute. If the null is true, we could get results like we got or even more extreme 26% of the time. That's not rare at all. So if it's not rare, we don't reject the null. Specifically, is our p-value less than alpha? Well, what was alpha? Right? 0.01. 0.2578 is not less than 0.01. We're not going to reject the null. The beauty of a p-value is it's more precise. We're saying this could happen almost 26% of the time. If you're doing the classical approach, you're saying, does this z-score, is it bigger than the other one? It's a yes-no thing. This is yes-no, but it gives you more details. Like, how far away are you from being there? If your p-value came out to be 0.02, then you'd be going, well, that's getting pretty close. But we're not even anywhere close on this one. All right, so decision time, since the p-value is not less than alpha, we can't reject the null. We're getting the same results. We're not going to reject that null. It's the same problem, just done two different ways. So the conclusion is going to be exactly the same. I wrote it out, but you don't need to. It's the same conclusion. Those two approaches ought to give you the same result. Either I'm going to reject the null or I'm not. We never say, oh, that means the null must be true. No, it doesn't. Just because a court finds somebody not guilty doesn't mean they were innocent. They might have done the crime. There just wasn't enough evidence to prove that. All right, let's look at example 2. Give you a minute to read that. So way back in 1994, 52% of parents thought that their high school kids were not getting enough math and science. We want to know, are today's parents, do they feel differently? Now, what does that mean? It means, well, it could be more than 52% want more math and science, or it could be less. It's just different. And alpha is 0.05 on this one. So first thing we ought to do is get p hat. Now look at those results. This is now, in 1994, it was 52%. That's a 20% jump. That feel differently. It might mean that more parents, but it doesn't look like it from this. This is a two-sided test. So now, what are our hypotheses? Well, our null is okay, now the P here is a population parameter. Which set of parents are we talking about? The 1994 parents or the 2025 parents? Yeah, you're right, the 25 parents. We know about the 1994 ones, don't we? Sure. So we're trying to make a test about today's parents. So if that comes out to be 52%, then we know today's parents don't feel any differently than the 94 parents. So the opposite of that, our alternative hypothesis is, notice this says not equal. This is a two-sided test. Today's parents are just different. The concerns about math and science have changed somehow. Could be more, could be less. From our sample, it looks like less, but still a two-sided test. All right, so alpha and your hypotheses you know before you ever get people in your sample. So then we look at the conditions. Yes, ma'am. That's a good question. Look back. Right here, do parents feel differently? If that word different is in there, that's the red flag that you're doing a two-sided test. Otherwise, it'll say more than, less than, those kinds of things. Good question. Okay, was our sample random? Yeah, probably. This was a major survey. Now, every time you do a hypothesis test, should you check these conditions? Yeah. Doesn't take but a second. Is our distribution normal enough? So we do our NP times 1 minus P thing. And notice again, I'm using that 0.52. Because why? We're assuming the null is true. We're saying, okay, let's just take what you've got. If the null really is 0.52, then that's what I'm going to use in my calculations here. If you can really make 90% of your free throws, I'll take you at your word. Come show me. So 199 is a lot bigger than 10, so we know that it's normal enough. And then are the people in our sample, are they independent? Well, yeah, 800 is way less than 5% of the number of parents today. 3 hoops, got to jump through all 3. If we got 400 students here. If I got a sample of size 100, the people in my sample wouldn't be independent anymore, right? Because that's 25% of the population. So then we'd be getting brothers and sisters and things like that. Might not be independent anymore. All right, so then we get a z-score. Again, notice I'm using the 0.52 from the null hypothesis. And if you look in your formula pages, it'll say p there, not p hat. So every place you see a 0.52, we're talking about the null hypothesis. Here's what I got. Check and see if I'm close. I'm pointing out something here. That's negative 11 standard deviations. How far out is that? That's off the charts. Based on your formula pages, could you get a p-value for that? How far do your formula pages go? Plus or minus 3.4 standard deviations, maybe? You're not going to get it from that table. Now, you can do it on a calculator. When I did, I think I got 1 point something times 10 to the negative 29th. So basically 0. The probability of getting that far out, if the null is true, is pretty much 0. Remember, the p-value is going to be a probability. So what's our critical value? Remember, alpha is 0.05, but this is a 2-sided test, so we have to split it in half. And that's why that little symbol z alpha divided by 2 is there. So 0.05 divided by 2 is 0.025. So where is the area 0.025? Now we're talking about, we ended up on the left-hand side of the mean here. Where is the area 0.025? I know it's going to be negative, but negative what? Z-score wise. So find the area as close to 0.025 as you can. And what's the z-score? Elijah? I'm with you. Okay. 1.96, negative 1.96 is the cutoff. We got negative 11. So decision time, here's my drawing. Here's 1.96 negative, here's 1.96 positive. We ended up on the negative side. Now remember, this is a 2-sided test. If I ended up in either of those blue regions, we would be rejecting the null, right? Where did we end up? Way out there. Way out there. We can't even see our z-score from the null. It's that far away. So what do? We say, well, our z-score is less than the cutoff point. So yeah, reject the null. Plenty of evidence to reject the null. Overwhelming evidence to reject the null. If this were a criminal trial, the defendant in the courtroom stabbed the victim 97 times. It's like, yeah, I think we better put this guy away. And then climbed up on the bench to try and get the judge. Yeah, we need this person off the streets. Okay, overwhelming evidence. So then what's our conclusion? Again, I'm stating the level of significance, what alpha is. And we got sufficient evidence to reject the null. And this time I can say, but I'm going to accept the alternative that today's parents are different in their concerns about math and science. which was the original question, right? Are they different? It looks like from our sample, 20% fewer parents are concerned about math and science. Interesting. Notice this doesn't get into the why. Okay, we good? So we did a one-tailed test, which was a right-tailed test. We just did a two-tailed test, but I want to show you something about these two-tailed tests. We're not going to do a p-value because that'd be silly. Same problem. You don't have to read it. We just worked it. But this time I want to do a confidence interval. Yeah, it's going to be easy. So I get p hat again. Pretend like we're back in chapter 9 and we're doing confidence intervals. What did we do there? We got what p hat was. We got what the critical value was. And in our tables, they gave us a critical value for 0.05, didn't they? If you check, it's there. So I just plug in my scores. Now, here's something different. Notice I'm not using 0.52. Why? Peyton says because that's what the formula says to do. Yeah, I can't argue with that. But why would the formula say to do that? When we're doing a hypothesis test, do we have some idea where the population parameter is? Yeah, somebody's telling us. It's 0.52 on this problem. When we're doing a confidence interval, what are we trying to do? We're trying to guess where that population parameter is. Nobody's telling us. We're trying to guess it based on our sample, which means what? We're going to use the results from our sample. That's all we've got. There's nobody telling us, oh, it could be 0.52 here. They're not telling us for a confidence interval. We're basing our guess on the sample. Okay, so when I do the math here, here's what I'm getting. Based on our sample, we're 95% confident that between 28.8 and 35.2% of today's parents think their kid's not getting enough math and science. Right? So let's draw that out. And again, I just want to remind you this is today's parents that we're estimating. We know what the 1994 parents felt. All right, so there's p hat. Here's my confidence interval. We're saying we're 95% confident that the true population parameter of today's parents is in here someplace between 28.8 and 35.2% that are concerned about math and science. Where did what was the null hypothesis? 0.52. It's way out here. Now think logically. When we did the hypothesis test, alpha was 0.05. When we did the confidence interval, it was 95%. We're going to reject the null. Look, the null is nowhere close to being in our interval here. We're saying we're 95% confident it's in between these two blue lines. That falls way outside of those blue lines. So what are we going to say? No, we're going to reject the null. If we're 95% confident it's here, then we're going to have to reject it because it's way out there. So the point is, if you've got a two-sided test that you're doing a hypothesis test, you'll get the same results if you do a confidence interval. So a two-sided test where alpha is 0.1, you do a 90% confidence interval. And what if the null, what if this 0.52 had been 0.33? That would have put it right here. Can I reject the null there? No, because I'm saying I'm 95% sure it's in there. It being the population parameter that we're trying to guess. I hope you understand the logic of that. For a two-sided test, this works out really nice. You could use a hypothesis test or a confidence interval. There's also ways of doing it with one-sided tests that we won't get into. If this were AP stats, we would. But it's not. Okay. Questions about today? That's it.